and his talk is going to be on flexural gravity wave scattering due to seabed undulation in the presence of multiple propagating wave modes. So if you could please start, Professor Sahoo, that would be fantastic. You're on mute currently, so that's not going to work so well, but unmute and take it away.
Thank you, Professor Milan. Am I audible?
Yes, you're audible. That looks great. That looks perfect.
Okay, thank you. So today the title of my talk is on flexural gravity wave scattering due to seabed undulation in the presence of multiple propagating wave modes. So these are the outlines of the talk. I will first provide a motivation and objective, give an introduction to flexural gravity waves, mathematical formulation. I'll just give a bit about the dispersal relation, then the solution method, then some of the results we have obtained, and then finally acknowledgement. So some of the motivations, basically, my previous speaker, Professor Yuri, has already talked a lot about wave-ice interaction problem, although non-linearity was included, but these problems, some of the major global issues in the 21st century is population growth, scarcity of land space, efforts to utilize ocean space. In addition, we have climate change due to global warming, sea level rise, and rise in the frequency of storms, and their impact on countries having large coastline. So as a result, there is another issue is that land reclamation for utilization of sea space in countries with lengthy coasts and very large floating structures are an alternative to land reclamation. So in addition to this, development of multipurpose facility in the context of exclusive economic zone for promoting blue economy. In this context, there are two approaches for addressing problems of future sea level rise and its impact. One of these is understanding wave ice interaction problem in the polar region, including the marginal ice zone, to understand how the wave ice interaction takes place. The other aspect is co-design and co-build coastal climate services for addressing the high-end risk due to sea level rise following United Nations mechanism for climate change compensation, adaptation, and prevention. So there are twofold approaches. There are two issues here. One is the wave interaction with very large floating structures, and another is the wave interaction with the floating ice sheet. Both have the commonality of the both class of problems is that we use for the structure, we are using the Euler-Bernoulli beam equation, or basically it's considered as a floating elastic plate model is used. So the objective of the presentation is to analyze the scattering of flexural gravity waves due to seabed undulation, especially due to a submerged tape and that of a submerged breakwater. Here, the main objective is to demonstrate the role of multiple propagating wave mode on flexural gravity wave scattering, which arise due to blocking of flexural gravity waves. The energy balance relation in the context of blocking dynamics is derived, and that is arising due to the presence of the multiple propagating wave mode, which is used to, and this result is used to validate the computational result for the scattering coefficients. So, although it is very well known, but I just give a brief introduction to flexural gravity waves. So basically, when the gravity wave interact with the flexural waves in a thin elastic plate, it gives rise to a special kind of wave, hydroelastic wave, what is known as the flexural gravity waves that propagate along the elastic plate. And such waves propagate when gravitators interact with a very large floating structure like a floating airport or a large floating ice sheet. So these are some of the examples. It is although one. Now I'll come back to the problem. Here the model I am considering is a two-dimensional fluid domain. The fluid is assumed to be inviscid and incompressible. The flow is irrotational and simple harmonic in time. And here, as I mentioned, the structure is modeled as a thin elastic plate with the inclusion of lateral compressive force. This is a generalization of the kind of Euler-Bernoulli beam equation. So the fluid is assumed to be homogeneous, and here the water depth is considered to be finite. So we have the existence of the velocity portion phi, and I can separate it in the spatial component of the velocity component and the time component, assuming the motion is simple harmonic. Similarly, the plate deflection is also separated. making the spatial component and the time dependent component, harmonic motion. So now in this context, we'll have the Laplace equation. The governing equation becomes the Laplace equation. This becomes our linearized free surface condition, that is the kinematic condition, and the plate covered boundary condition is this. And then this becomes the plate covered boundary condition, particularly in the linearized version, and the various coefficients are already mentioned here. So then, assuming the seabed is rigid, we have two parts. One is the undulated part. Basically, I just consider a state. So I take the normal velocity 0, the seabed. So then we have the continuity of velocity and pressure along the edges. Basically, I will rather go to the if I go back to here, if I take the interface condition here and the bottom bed at the free surface, I have already the plate code condition, the continuity of velocity as pressure along the interface, and at the edges of the structure, I will have the four conditions that will be satisfied here. These are the continuity of plate deflection, slope of deflection, bending moment, and shear force that will be there continuous at the plate when the two plates at the joint where the two plates interact with each other. And then the far field condition, assuming that there is a single propagating mode, the far field behavior is the incident wave part, this is the reflected wave part, and this is the transmitted wave part. Here, this is based on the assumption that there is a single propagating wave mode exists. Now, if I look at the plane wave characteristics of this class of problem, then I take zeta j as in the time zeta j x e to the power minus I omega t, and zeta j can be written in this form, where j can be 1, 2, 3. It can vary from 1 to 3. So here I am assuming 3 waves, and I'll talk about it, how the 3 waves are, 3 propagating modes are coming here. So in that case, the corresponding phi j's are these, and this becomes the dispersion relation, which in the non-dimensional form is given by this. This is the non-dimensional form of the dispersion relation. And then if I'll go to the corresponding the dispersion relation in the case of infinite water depth, assuming case is large, then this becomes the dispersion relation. And in this context, we can see that if I plot just omega versus k, basically the dispersion curve, I will see that unlike the case of gravity wave, I will see here there is a different pattern is observed. At A, we will have 3 roots colliding at the point A, and that is called the saddle point. Whereas at the point B1 and B2, we will see that the maxima at B1 and minima at B2 occurs here, d omega by dk is 0. Double root, there was occurrence of 2 roots colliding at these 2 points. On the other hand, between any point between B1 and B2, we can see that if I draw any line like this one, then I see that it cuts the axis at this curve at 3 points. That means 3 propagating modes exist here. So these are the point B1 and B2 are called the blocking point. A is the saddle point. And any point between B1 and B2, if I, for any frequency between B1 and B2, I can have 3 propagating modes exist. Unlike the case of gravity wave or flexural gravity waves, where we used to get only one single propagating mode. But here we are finding that between B1 and B2, between the blocking frequencies, we have 3 propagating modes. So in this context, the scattering problem has to be looked into properly so that we accommodate the 3 propagating modes. This is what my objective. And here I plot CG versus K, then we can see that between this B1 and B2, the energy flux becomes negative. And at this point P, this becomes discontinuous. So this is the point of the point where it is discontinuous. This is the blocking point where the wave blocking occurs, and this B1 and B2 are the blocking points. But between B1 and B2, the energy flux is negative. So these are some of the observations. This was published paper in Proceeding Royal Society of London in 2017. And now this concept we are taking, now I just in the context of the present problem, I have 2 variations in water depth, that is H1 and H2. So if I just take Q is equal to 1.4 D, Q is the compressive force. So we can see that almost the omega versus K, if I plot it here, everything is quite normal. That means only one single root will occur. But if I increase Q to 1.9 into root D, where Q is the compressive force, D is the rigidity of the structure, then as I mentioned earlier that in case of in the reflected region, we'll have the red line. Here also we have 3 roots, and also in the transmitted region also we can see that there are 3 roots. So that's what I have already mentioned. And now in this context, the far field boundary condition, in case if there is a single propagating mode, the far field behavior is of this form I have mentioned in the beginning. So I1 is the incident potential, incident wave amplitude, and R1 is associated with the reflected wave amplitude, T2 is the transmitted wave amplitude. On the other hand, if I consider the 3 propagating mode as we just now I mentioned, then the generalization of this radiation condition can be because 3 incident wave will be there can be and corresponding. But here at a time we'll consider one of the incident wave. First I just say that if I note is the incident wave, it can induce a wave, reflect 3 reflected wave as well as a 3 transmitted wave. Similarly, depending on whether I take I1, I2, or I3, then, but in the context of the present problem, we are considering only incident wave can be either I1, I0, or I2, because between I1, if I look at this one, because the direction of propagation is positive in this direction, but between these 2 blocking point, where the solution is I consider as I1, there the direction of propagation is changing. So this cannot be, because here CG will be negative and this cannot be considered as incident wave. Provided, since we are considering I1 and I3, I2, they can be considered as incident wave. So however, the corresponding reflected and transmitted waves for the 3 propagating mode can be induced because of the either I0 or I2. I2 cannot be an incident wave as long as the direction is concerned. But if I consider I2 as incident wave, then I1, I0, and I1 cannot be considered as incident. Because so with this, this is the basic philosophy. And with this phi1, I just expanded since I'm taking either I0 or I2 as the incident wave. So with this assumption, I take my phi1 as expanded in this form in the using eigenfunction expansion method. Similarly, phi2 is expanded. And now this is the corresponding FNY. But one of the beauty is that complexity comes in. What about FJN? These FJN, they are not orthogonal in the classical sense. Thus, we introduce another set of, this can be another set of orthogonal function in the subsequent discussion for solving this problem and obtaining the constant. Here I look at the surface gravity wave, the vertical eigenfunction associated with the surface gravity wave problem, where omega square is Pj. And these eigenfunctions are orthogonal in the classical sense. So what we are using, will couple the matching condition will apply and use the orthogonality, multiply this with the, in fact, in this sense, I multiply my Fn's are the eigenfunctions with associated with the flexural one, where Gn's are the associated with the gravity. So I just use this orthogonal set of function to develop a set of orthogonal set of a system of 2m plus 6 equations for the 2m plus 6 unknowns. And this becomes much easier than the using the modified eigenfunction which earlier has been developed, because that looks a little complex, but here it has made our life simple. And this method is quite well known. Introducing another orthogonal set of eigenfunction is very well known in variational calculus, variational friendship particularly. And this concept has been borrowed here and used to solve this class of problem. So, and then we got a system of equation, and 2m plus 6 is system of equations for the unknowns. And then the corresponding energy balance relation here I give, particularly assuming either I is 0 or 2, we can see that the energy balance relation takes this form. And in this context, the KR's I square is chi 10 into this minus chi 1i into this. So this is the detail where chi rj and chi tj are given by this. So now these chi ri and chi ti, they are actually the modified reflection coefficients. And it has 2 components, because this chi pj here, that is basically the ratio of the energy transfer rate. So these together satisfy the energy identity in this. In the simplest case, and this is for assuming that whether I consider I is 0 as the incident wave or I is 1 as the incident wave. On the other hand, if I say that if it is single propagating modes, this becomes much simpler because this one of the higher modes, the multiple modes will not contribute, so it will be much simpler as it is well known in the classical sense. So now one propagating mode, one or three propagating mode, this becomes this also. And in case of single propagating mode, this is the simplest one is this, and here this KT is this and Ki is this one. This is well known. This is modified energy balance relation. Now with this, I will now take up, I just come the reflected wave omega versus kappa in the reflected region and in the transmitted region, how this dispersion relation behaves, and particularly the corresponding Kr and Kt, particularly in case of single propagating mode that occurs prior to the blocking. And here it is, this is the pattern of the reflection and transmission coefficient. On the other hand, when I next we considered within the blocking frequency, that means omega, what we call this primary blocking and secondary blocking within this frequency. We can see here in the first figure, I have taken the divided the whole region that depending on the water depth and the number of propagating mode, I divided into 5 regions. In region 5 and region 1, I have only single propagating mode, whereas in region 2, because of the bottom undulation and the blocking frequencies, I just say that Z2, Z3, Z4, this shows how the behavior of the propagating modes, number of propagating modes occurs. So we can see that in 3 roots in TS and 1 in RS in Z2, or in Z3, we have 3 roots in each R3 in the reflected side and transmitted side, where in Z for 1 root on the transmitted side, you have 3 roots on this. So in fact, these are the frequency and the number of roots we have mentioned here. Taking this data, now I'll analyze some of the results. The reflection coefficient we have taken here, and again we are plotting in the propagating mode, depending on which region and how many propagating modes are occurring. We have plotted the reflection coefficient as well as the transmission coefficient. We can see that in region Z1, this is the between Z1 where one single propagating, then we have Z2, 3 roots in the transmitted side, where it's 1 root in the reflection side. And here, in fact, we'll see that at the point where there's a jump discontinuity, and this kind of discontinuity occur due to the blocking, occurrence of wave blocking. And similarly, in the case of a transmission also, we have the similar situation occurs, and because we take the appropriate propagating modes in the individual regions, and then the pattern of the reflection and transmission coefficients are plotted. Now this, now we just look at the corresponding time domain simulation of the plate deflection, and here it's a glimpse of the plate deflection and the irregularity in the pattern that is very obvious in the because of the propagation of the multiple propagating modes. And this is a case of a state. Now I generalize this in brief that for a submerged plate or a submerged trench, this result can be generalized using the theory of symmetry. We can write phi s and phi a in this form. And then we have the corresponding phi 1s, phi 2s, phi 1a, phi 2a. They're expanded in this form following the same approach. And then we have then the phi plus and phi minus, they are obtained, it can be obtained from this. And once we know phi 1s, because already I'm using the single, the undulated bed result, and directly I'm getting the solution phi plus and phi minus in case of a stepped, in case of either in the wave scattering due to a trench or due to a breakwater. And then the corresponding KRG, KTJ are obtained, and the appropriate energy relation is also given here. I'm not again repeating the same stuff, but it's the calculations are done. So now, if I just take the result of a submerged plate, and the case of a submerged plate for 3 different cases, Q is equal to 0, Q is equal to 0.5 and 1.2. This is prior to blocking. Multiple propagating modes are a single propagating mode, and number of zeros in the KR and KTs are observed here. And on the other hand, if I take the same result within the blocking frequency by considering Q is 1.9 root D, then you can see the within this range, we again see that at the occurrence of the discontinuity at the blocking points. And then the propagating, the number of zeros are there, but at Z close to Z2, Z3, and Z4, we can see that the discontinuity in the reflection and transmission coefficient occurs, and that is due to the blocking of. Now the same result is again in the time domain simulation. This has been done, and we can see the irregularity pattern in the wave propagation, and here this irregularity is coming due to the superposition of 3 propagating modes, or 2 propagate, or depending on 3 propagating modes on the reflected side or the transmitted side, and or depending on the number of propagating modes, this also changes, the pattern is changing. So this I will conclude my talk, and this part of the presentation is a part of the manuscript which is recently published in Physics of Fluid, and I thank my co-authors, Dr. Susam Bural, Professor Michael Mellon, and Professor Bhavani for contributing to this paper and collaborating me in this work. Thank you all for your kind attention. This is a book which quite 10 years back I published on mathematical techniques and for wave interaction with flexible structure. We are in the process of compiling another book in this. Thank you much. Thank you so much for your attention.
Thank you very much, Mr. Sahoo. That was a great talk, and also kept perfectly to time as well. So do we have some questions? I feel like it's a bit hard for me to ask questions about this. All right, some people, again, feel free to write some question in the chat. I wonder what whether it's interesting to see what Pawan's doing next, but we could turn this problem and make it into a circular one really easily as well, I would have thought, right?
Yes, yes, we can do. In fact, we are working on a similar problem. At present, we are working on a similar problem on circular trencher. Because there we will take instead of the eigenfunction expansion, it will be Fourier Bessel series type of expansion, and we can generalize this work.
Yeah, no, exactly. And then you could, I mean, there's no end to the fun. You could include multiple ones and use Graf's addition theorem.
Yeah, thank you.
But yeah, because, and what about, this kind of scattering matrix approach? If you had multiple of these,
yeah, because of multiple, because actually these are the propagating modes. That will be, the solution will be unbounded, because if I take the double root or triple roots at the blocking point or at the point of inflection, the expansion, there will be some kind of unboundedness behavior will come in this expansion. In fact, we have got the solution, but then because of the unboundedness characteristics, if we include them, the unboundedness behavior, then we will not get a very fruitful solution. That's why this aspect we are not considering. Rather, we consider the multiple propagating modes which are distinct in nature, but not, if they coalesce, then the solution will be diverging in nature, and that solution will not be very useful for us. So we are not.
Yeah, because you don't really have any propagation of energy. Yeah. But what about having multiple, if you had multiple structures and you used a scattering matrix?
Yeah, in fact, multiple structures will be okay, fine, no issue, because then we may come across situation like drag scattering. And the concept is, I think we had earlier some work on trenches. The same concept, we can always generalize this from single to multiple. Trenches are breakwater multiple. Directly, we can do it by simple way of, if we assume that objects are very far apart from each other, we can remove the Evanson mode and apply the wide spacing approximation to get a quick solution. But otherwise, it will be a large computational. If we include the events and modes, then the solution matrix system will be very large. Otherwise, we can do it by wide spacing approximation.
But if you did the wide spacing approximation, you'd need to have more than one propagating mode. Yeah.
Yes.
I'm not sure that I've ever seen that, but anyway, yeah.
Anyway,
all right. Now, I'm hoping to get another question here from someone in the audience, but if there's no other questions, we maybe just pause for a few minutes. We'll have a break for 5 minutes, and maybe it's a good time to have a break as well. And then is there any other questions here? Not seeing any other questions. All right, so we can have a break for a few minutes. You can have some chit chat if you want, and then we'll get Pawan to start in